Where do you think you're going? Come back here now. This is a tutorial on limiting movement. Let's get started. It is gone, off screen entirely. And if we go to the other side, we can see that the ship has decided that it doesn't want to be with us anymore. There's no more interesting over here. So here we are inside our fleeing object. What is currently happening is that the movement function here is being called, and into that movement function is a calculated movement vector, vector 3, and that assumes the total movement that we're going to want to be applied to that object, which is currently why the object thinks that it has the liberty of leaving us. That's what we're going to have to go and change. We have the total movement, and the total movement is considered to be the input on the x value multiplied by movement speed multiplied by delta time, and that in its entirety is then being passed into transform.translate through the movement function. So after this point, we're going to want to add a few checks to simply limit the movement. And the checks require us to be able to predict where the movement would take us if it were immediately applied to the transform. So what we're going to do now is add the total movement to the transform and then check the x position of that transform to see if it takes us into the undesirable areas, or in this case, off screen. So we're going to create a new vector 3 called movement if applied. And that's going to be equal to the total movement value we have above added to our transform.position. Next, we'll check the x position on the movement if applied vector to see if that would take us out of the screen if it was applied through transform.translate. I already know that the boundaries of my screen are met when the ship moves to the value 38. If you didn't want to hard code it into your script, you could always serialize a field and add it in the inspector, or add another calculation here to calculate where you would want your boundary to be. This is where it would be called. Now flip the values within this statement in order to get it to work with the other side of the screen too. So now we should have a nice implementation here, a simple implementation of movement restriction. And I am not moving at all. Let's see what I've done. Ah, yes, I forgot to flip the sign here to be less than. Otherwise, it will always be true, I guess. And here we are. It's now working. Let's remove my big head. Now, ship is looking rather good. We have a simple implementation of movement restriction and limitation, but I want to refine this just a little bit more because this won't be quite as accurate as required once the movement speed becomes greater or perhaps exaggerated. So if I up my movement speed here greatly, it no longer pushes flush with 38. It would previously stop around 37.99, and it still does on occasion, but it's no longer guaranteed. So I want a guaranteed number for when it restricts the movement, no matter the speed. So we're going to set the x position on our transform components just before the movement is stopped entirely. That way we can ensure that the position that we're left with, or left on, will always be a specific distance to the maximum or minimum threshold. So just before the return, which returns vector 3.0, we're going to set the transform position to a new vector 3, putting in a 0 for z, 0 for y, always with the floats, and 37.95. I think that's nice and flush enough. And then also copying and pasting it into the negative version, keeping our left side nice and clean as well, having negative 37. And let's just test that. So you can see that on either side, it stops at the values given and remains reliable even when passing in absurd values. Always 37.95 to the negative or to the positive. And that's excellent. Leave a comment and let us know what you thought of our tutorial. This tutorial is based on a game that I'm currently creating with my son. Click here to see more. Don't forget to like, subscribe, and ring the bell.